Harry from GMAT Ninja here, and in today's video we're going to talk about arithmetic on the GMAT. Or we might say that this is one of the worst named videos in this series because we're going to talk about how to avoid arithmetic on the GMAT. What we're going to look at is what to do when the GMAT throws something that looks intimidating at you, or when midway through your solution you get to a horrible division or a horrible calculation, horrible multiplication, and what you can do to make that a bit simpler. Now, to do that, I've got 6 questions coming your way. The first 4 of them are not going to be that tough. We're probably looking at somewhere between a 75 and an 80 on the scoring level. Then question 5, we're going to dial the difficulty level up a bit. We're going to get into the 80s, and then question 6, we're going to put a real challenge on you, and question 6 will be tough. Now, having said that the first part of the video is not that difficult, please stay with us because some of the concepts we're going to look at are going to be some of the most important you see in throughout the entire series. One of the worst things you can do on the GMAT is to miss a question that you know how to do, and really the calculations are the bit that you know how to do. If you've broken through the concept, if you've understood the question, but you mess up the multiplication or division somewhere, you're really losing points that you should be getting. So today's video, while it's not going to be that tough, is going to be really important. We do have one data sufficiency question in there. It's going to be the final question. We know that data sufficiency is now on the data insights section, but it's still using the same math concepts underpinning it, so we're doing them together in the same video. All right, without any further ado, I'll get the first question up on the screen. Take a couple of minutes and have a look at this, and I'll see you to look at the solution after you've had that time.
Hey everybody, Charles here. Sorry for the interruption. Before we get you back to that quant content, 3 quick things I'd love for you to be aware of. First of all, this video is part of our full, free, complete GMAT course that's available up on our YouTube channel. If this course is saving you money that you would otherwise spend on a course or a tutor, please consider donating some of that savings to charity, either a charity that you love. If you don't have a charity that you love, we've got a list of charities that we love to support on our website, gmatninja.com. Second thing, if you love that presenter that you're watching in this video, not me, the other one, they offer one-on-one tutoring. If you're interested in that, gmatninja.com and we can set you up. Third thing, finally, if you're doing great on the GMAT, doing great on the GRE, starting to look for admissions help with your applications for grad school, we would love to refer you to a bunch of our favorite companies. So just hit us up. There is a contact form on our website, gmatninja.com. Also, a link in the video description. Just fill that out. We'll send you a list of our favorite admissions consultants, not just at our company, no strings attached, not going to sell your email, not going to try to sell you anything. We just want to make sure if you've put in the hard work on the GMAT, that you end up in the best possible hands if you need help with your applications. All right, that's it. Enjoy the quant.
Okay, question 1. Hopefully that wasn't too tough, but if you want a bit more time, feel free to pause the video here, go back, rewind, watch the question again. We'll still be here going through the solution once you've had a bit more time to take a look at it. But let's get into it for now. So we've got this crowd of 40,000, they're watching some football game, and this family of four has to leave. Their child's had a bit of a tantrum. And the question that we really want to ask is, the number of people in the crowd after the family leaves is how many times the number of people in the family. So that final sentence, that gives us the ability to set up a bit of an equation here. So the number of people in the crowd, we could say that's 40,000, but the number of people in the crowd after the family leaves, so this family of four has disappeared, has gone away. That is how many times the number of people in the family. So that is equal to, the number of people in the family is 4, but we want to know what we need to multiply that by in order to match the 40,000 minus 4 on the other side. So at this point, 40,000 minus 4, that's not difficult. I'm going to jump straight in. 39,996 is equal to 4x. So in order to find the value of x that I want, the multiplier that I'm looking for in this question, I need to do 39,996 divided by 4. Now, this is what I want to get into in some of these videos. This, admittedly, is not the most difficult calculation, and yeah, I'm sure that loads of you have got the right answer to this, but this is the principle that I want to get to. This doesn't look nice, and in the question you might get at, there might be something that's even nastier than this. So what can we do about it? Well, I'm going to come back to this line and sort of branch off, and we'll go to one side. Yeah, the subtraction was the obvious thing to do first, but maybe it wasn't the best thing to do first. If I rewrite this over here, so we had 40,000 minus 4 is equal to 4x, and then think maybe I do the division first. So my x value, that's going to be 40,000 minus 4, all divided by 4. Now what we can do here is we could split this up, so I can split the top of a fraction up. Just to be careful, I can't split the bottom of a fraction up. If this was the other way around, I wouldn't be able to separate it. You can only split the top of the fraction up in this way, and we could say that's 40,000 divided by 4 minus 4 divided by 4. Well, 40,000 divided by 4, that's just going to give us 10,000, and 4 divided by 4, that's just going to give us 1. And so the final answer we're going to get here is 9,999. And so C is the answer to this question. Now, as I said, look, that is hopefully an easy question for you. But the thing that I want to focus on is that principle. What can we do to make this calculation a bit simpler? Maybe I don't just want to think about kind of bashing my face into the wall and doing a really nasty division if I don't have to. Maybe I can find a way around it, do 2 divisions. Yeah, I'm going to do 2 processes rather than 1, but each of those processes are going to be simpler, and the most important thing, I'm less likely to make a mistake in doing them. And I get to the answer, yeah, maybe it takes me 5-10 seconds longer, but as I say, I'm not going to screw this up, or I'm going to be less likely to screw this up than I am doing something horrible. All right, that's the sort of principle I want to carry through in these videos. So next question's coming up, give you 2 minutes, have a go at this one. All right, another question that on the surface of it isn't that tough, but the numbers, the calculations are going to make it look more difficult than it really is, because what we're asked to do, we want to find the arithmetic mean. We want to find the average cost of a ticket. So, I mean, conceptually we can think of that. It's quite simple. I want to know the total cost of all the tickets and then divide it by the number of tickets available. So we can set that calculation up. The average, the thing that I'm looking for, well, I want the total price of all the tickets. So working them through at the silver level, I've got 4,000 tickets and they're $50 each. So the total cost of the silver ticket is going to be 4,000 times by 50. And then I do the same thing for all the other tiers. So gold is going to be 3,000 tickets times by $100 each. Platinum is going to be 2,500 tickets times $150 each. And the diamond, I've got 500 tickets multiplied by $250 each. And then I need to divide that whole thing by the total number of seats that we've got going on. So that's 4,000 plus 3,000 plus 2,500 plus 500. And so we end up with this, which is right. Nothing has gone wrong here. That this is the right way to do it, but yeah, the calculations are going to build up pretty quickly. I don't really want to do 4,000 times 50 and then do, I don't know, 3,000 times 100 isn't that tough, but you can see that the amount of time this is going to take is going to build up very quickly. What I could do instead is look for common factors. Now this becomes a very big thing on the GMAT. It's quite common, it's surprisingly common. It's just maybe we don't see it as often as we could. There's a common factors in each of these. The number of seats at each tier, well, they're all multiples of 500. So I could pull a 500 out of the front of this calculation and this whole thing suddenly will become a bit simpler. I've got 8 times 50 plus 6 times 100 plus 5 times 150 plus 1 times 250, and I could do the same on the bottom of this fraction. I've got 500 and that's now 8 plus 6 plus 5 plus 1. Right, so I think things are looking a bit nicer here, and yeah, we can go ahead, we can cancel the 500s. Then what I could do again, right, bottom line, yeah, I'm just going to add these numbers up, but top line, we've got multiples of 50 here. You might not need to do it at this stage, but maybe the calculation, the question you're doing, or in a different question is going to be a bit tougher. And yeah, we can keep factoring things out. So top line, let's factor out a 50 here. So I've got 8 times 1 plus 6 times 2 plus 5 times 3 plus 1 times 5. And bottom of the fraction, yeah, I'm going to add these numbers up. So 8 plus 6 is 14, plus 5 is 19, plus 1 is 20. So now I've got 50 multiplied by 8 times 1 is 1, 6 times 2 is 12, 5 times 3 is 15, 1 times 5 is 5. All of this is still over 20. 8 plus 12 is 20, 35, 40. So I've got 50 multiplied by 40 divided by 20, and I can start to cancel things. 40 and 20, they cancel, so 40 is 2 times 20, so the whole thing simplifies right down to 50 times 2, which will give me 100, and so my final answer for this question is B. All right, again, same with the last question. I don't want to focus too much on this question. There are loads of different ways of answering this question, and if you had a different solution, please punch it into the comments. The more different ways of solving a question like this we've got, wonderful. The thing that I want to focus on is this, again, the principle of, look for common factors, see if you can pull them out the front, stick a set of parentheses in, rewrite your equation, but the calculations that you do inside that equation inside that set of parentheses are going to be simpler. That's the aim we're doing here. We want to take what look like horrible calculations and make them into something simpler. I would far rather do 8 times 1 and 6 times 2 and 5 times 3 than I would something like 2,500 times 150. This is going to take some time. Okay, writing a few lines out is going to take a little bit of time, but it's going to be far easier for me to do 5 times 3 than it is 2,500 times 150. And that's the sort of thing I want you to take away from this video. I want you to think about. All right, we're going to keep these rolling. Question 3 is coming. Take a couple of minutes to have a look at this one. All right, another nasty looking question. Hopefully the calculations aren't going to be quite so bad after we've done a bit of work on it, but yeah, not nice looking to begin with. As always, if you want a bit more time, now's your chance to pause it before we really dive into this, but yeah, let's take a look at this one. So the first thing I want to notice here is that we're not asked for a precise answer. We don't want to know whether P is going to be, I don't know, 0.2341 or something quite so precise. We just got a range. Now what that means is with something that looks like this, something that looks so precise, we don't need to be quite so accurate with it. I can do a bit of estimation, I can do a bit of rounding here. So let me take that top line, 0.7197, that's really close to 0.72. So let me just simplify that a little bit. I can't move it too far, but I can estimate it a little bit. And we can do the same with a couple of these other bits. So 0.294, that's very similar to 0.3, and 0.739, let's call that something very similar to 0.74. So we've taken something that looks awful and made it look that little bit nicer, but it's still not great. I don't like the decimals. That's the next bit I'm going to deal with here. Now I'm sure, yeah, we've all seen something like, I don't know, if x is 54,000 over 2,000, well then I can take this and I can start cancelling out zeros and we can make the numbers smaller. But what you don't often see is we can go the other way and make the numbers bigger if we need to. So if I take this, if I look at the 0.72 and the 0.3 first, I can times both of those by 10. I can times top of the fraction by 10, bottom of the fraction by 10, and that will at least give me a whole number here. So my top line is now going to be something like it's going to be something like 7.2, and the 0.3 is now going to be 3, and I've got a whole number there. I like whole numbers. Whole numbers make this whole thing nicer, and I'm still with that 0.74. So if I want to get rid of the 0.74, well, I'm going to times the top and bottom of this fraction by 100 to make that 0.74 into a whole number. Now top line, if I multiply that by 100, I'm going to get 720. I've still got the 3, and the 0.74 is now 74. And now we've taken something that looked horrendous up at the beginning, and it's still not nice. I still don't really want to do 720 divided by 74 divided by 3. It's still not wonderful, but it's much better than it was. And now our next job, we're just going to go and simplify this step by step. There's loads of different ways of doing this, different orders, however you want to do it, totally fine. But what I would say is try and make these steps as small as possible. I don't really want to try and do long division of 720 over 74. It's going to take forever. It's going to be awful. If you can see it, we can spot that 720 and 3, they're both in the 3 times table. 720 does divide by 3, and what we're going to get there is 240 divided by 74. And from there, I'm just going to go step by step. I don't know what 240 divided by 74 is. I do know they're both even though, so let's divide both of them by 2. That's going to give me 120 over 37. Now 37 is a prime number, so I'm not going to be able to take this any further. But 120 divided by 37, that's something that I can begin to work with. What we could do is say, well, 37, if I times that by 2, I get to 74. If I add on another 37, I'm going to get 111, and the next one's going to be 148. So 120, well, that's going to be sitting somewhere between 3 times 37 and 4 times 37, which means that my overall answer here, this value of P, is going to be somewhere between 3 and 4, and D is going to be the answer to this question. All right, so a couple of different things going on there, and again, the order you do them in doesn't really matter that much. I estimated the first, so made 0.717 into made 0.7197 into 0.72 first, and then multiplied up to make them a whole number. You could do the opposite way. You could make them all whole numbers and then estimate and then simplify down. Here I did 720 divided by 3 first. You could do 720 divided by 2 and 74 divided by 2. You can do them in that order. The order doesn't really matter. Again, this video is all about the principles behind this thing. We're taking something that looks terrible, we're taking something that looks nasty and intimidating and making it into something that looks much nicer, which enables us to answer the question. All right, racing through these questions. Question 4 coming up now. Take a couple of minutes and have a look at this. All right, up till now in this video, it's all been about simplifying the calculations, and that's still going to be important in what we do. But here I want to think about sort of systematizing the process. I want you to think in terms of a process rather than just in terms of I've got to calculate, because we might look at a question like this. So which of the following numbers is closest to a half? And think, well, now I'm going to have to do something like a half minus 9/16 and a half minus 10/19 and a half and just, there's a lot of calculation in that. We're going to do something similar, but let's just think about how we could structure this in order to minimize the amount of calculation we need to do. And when we're looking at fractions, and certainly when we're thinking about either addition or subtraction of fractions, I want you to be thinking about denominators. How can we make the denominators the same in order to make the calculation as simple as possible? So what I'm going to do is, underneath each of these, I'm going to write the equivalent fraction to a half using each of these denominators. Now what that means is, so a half is equivalent to, if we're doing something over 16, it's equivalent to 8 over 16. So 9 over 16 is 1/16 away from a half. Now here we've got 9.5/19. Again, I'm not too keen on the 0.5 there, but we'll run with it for a bit. Now that means that 10/19 is 0.5/19 away from a half, or that's equivalent to 1 over 38 if I want to use nice round whole numbers, which I generally do. I like nice big round whole numbers. So 1/16 away for A, 1/38 away for B. Because the denominator, because we've got a 1 on the top, we've got ones, and we're going to get ones everywhere, the denominator on B is bigger than the denominator on A. This means that this gap, the gap between 10/19 and a half, is smaller for B than it is for A. A is not going to be the answer. Between these two, it's going to be B, but we've got C, D, and E to check. So denominator of 24, if the equivalent fraction to a half is 12, and so C is 1/24 away from a half. Let's keep going for D. For a denominator of 30, well, a half would be 15/30, so 16/30 is 1/30 away from a half. And finally, if I've got something over 36, well, the equivalent fraction 18 over 36 is the same as a half, so E, 19 over 36, is 1/36 away from a half. And now as I look across this list, again, I've got ones for each of the numerators here. Yeah, I had to do a little bit of extra work for B, but the reason I did that is so I can have ones in all the numerators, which means that what I'm looking for is the smallest gap between one of these numbers, well, the smallest gap between one of these numbers and a half, which is, I want the smallest of these numbers down at the bottom, and that is going to be 1/38, because the denominator is the biggest, because the 38 is the biggest, which means B is the answer here. Now again, we actually did a half minus each of these fractions, but because we sort of systematized it, because I just went, what is the equivalent to a half if I had each of these denominators, it made the whole process as simple as I could make it anyway. This is another question where I'm sure there are lots of different solutions, so if you've got a different way of doing it, please punch it into the comments. It'd be great to learn of a new way to answer this question. All right, those are the four of what we might call the more simple questions. We're going to start turning the difficulty level up a little bit. Question 5, it's not the toughest, but it's equally not the nicest. Think about the stuff we've done in this first 4 questions and try and apply those principles as we move into this one. We'll give you a couple of minutes and see you back here soon. All right, we said we're turning the difficulty level up, but the difficulty level here is a little bit more about just the intimidation factor than the difficulty of the actual calculations. Because again, looking at this question, I mean, the numbers that we're giving you, they just look awful. They're so big or they're so small, and there's a lot going on here. So if we're going to get to an answer, efficiently, sort of within the time we've got available on the GMAT, we're going to have to do a few things to simplify these numbers and make them look nicer, and really that's where we're going with this. Now, if you remember back a couple of questions, I said I don't like working with decimals when I can avoid it. I really want to be working with whole numbers, and that gives us a bit of a clue as to where to start with in this question. Q here, I mean, again, it doesn't look nice because 0.235, but it's got the least going on. I don't have to do a division or a multiplication, so I'm going to start with Q and say, well, 0.235 times 10 to the 12. Well, I want a whole number here instead of 0.235. I would need to multiply that by 1,000 or 10 to the 3 in order to make that a whole number. So I could say, to go through the steps, that's the same as saying 0.235 times 10 to the 3 times 10 to the 9. And this bit, 0.235 times 10 to the 3, that will give me 235 times 10 to the 9. Okay, so from now, I've just got a format that I can work with in here. Q is 235 times 10 to the 9, and if I can turn the other numbers here into a similar format, then I can start to compare them, and we might get something we can work with here. So let's take a look at P. Now, 400,000, that is the same as saying that's 4 times 1, 2, 3, 4, 5. I'm moving that decimal point 5 times, so 4 times 10 to the 5 multiplied by 5 times 10 to the 5, or in other words, I've got 20 times 10 to the 10. But to get it into that same format with the 10 to the 9 going on, I'm going to call that 200 times 10 to the 9. And so we've got those first two numbers here, and I can say that P is less than Q. So we could cross out a couple of the answer choices now before we move any further, but let's leave that till the end. I'm going to deal with R and S. Right, so R, first of all, 100,000 plus 25,000, we could say that that is 125,000, and we'll simplify that more in a second. 10 to the power of 3 to the power of 2. Rules of exponents would tell us that that is the same as saying times 10 to the 6 here. Now, 125,000, I could call that 125 times 1,000, or times 10 to the 3. And I've got times 10 to the 6 there, so R is going to be 125 times 10 to the 9. And that is the smallest out of the three numbers we have so far, so R is going to be less there. One more, S here. Again, so top line, 500 million, so that is the same as saying sort of, I'm going to call that 500 because we've been dealing with three-figure numbers in all of these. So I'm going to call that 500 to start with, but that's the same. I've moved the decimal point 6 times, or 500 times 10 to the 6. That's the same as 500 million. I'm then dividing that by 4 times 10 to the 1, 2, 3 times 10 to the minus 3 there. All right, so I could split this up, 500 over 4, and I've got times 10 to the 6 divided by 10 to the negative 3. 500 divided by 4, that's the same as 125. And rules of exponents again, I've got 10 to the 6 divided by 10 to the minus 3, so that's the same as 10 to the 6 take away negative 3. 6 take away negative 3 is going to give me 9, and I've got 125 times 10 to the 9 here. And so S is the same as R, which is less than P, which is less than Q, and now I just need to find something that matches here. So R is equal to S, which is less than P, is less than Q. C is going to be our answer to this question. All right, so big chunk of work to do here, and really that's where the difficulty comes. It's not so much the difficulty of the calculations, because we did 500 divided by 4 and we did 4 times 5. Okay, there's a bit of exponent work to go on, there's a bit of understanding of scientific notation, but the calculation's not that hard. It's the intimidation factor. If you can see a way into these questions, I went with Q first, you might have jumped in on P. Again, different ways of doing these questions, but if you can simplify it, if you can make the question look nicer to you and just work your way through it steadily, methodically, it's hopefully going to be not that bad. All right, final question for you today coming up, and we're going to take a jump in the difficulty level here. We need to challenge you a little bit in each of these videos. So here's your challenge for today. It's a data sufficiency question as well. So challenge coming at all different kinds of levels. Have a couple of minutes and take a look at this.
All right, two last things. Thank you so much for making it to the end of the video. If you've made it this far, you're one of those awesome people that's obviously really engaged in this GMAT thing. We would love your comments and your feedback. If there's anything else you'd love to see in our videos, hit us up in the comments. We'll do our best to oblige. Second thing, if you're enjoying it, hit that like button, hit the subscribe button. Helps other test takers like you find our full free video course. You need anything else? You know where to find us, gmatninja.com. Thanks so much. Enjoy this last question.
All right, final question here, and there's a lot going on in this one. We've got this great big wall of text. It's going to give us a lot of information, and we're going to get some fairly nasty calculations that we're going to have to manage. Basically, we're going to use everything that we've looked at as we've gone through this video so far. So let's jump in. Let's take a look at what we've got, and let's see what we need to do here. So situation is Bo's selling food. He's selling plates of hummus, he's selling packs of pita, and he makes a different amount of profit for each one. We get told that these are the only things he sold, and there's a total 214 plates of hummus and packs of pita. And the question we're trying to figure out, can we tell whether Bo's profit was greater than $700 yesterday? Now, from the first sentence, I can generate an equation for the profit. Bo's profit is going to be $6.06 for every plate of hummus. Now, we've got a lot of P's. We've got plates, we've got packs, we've got pitas. I'm going to call his plates of hummus H, and he profits 79 cents for every pack of pitas, so let's call those P. 79 cents for every pack of pitas. Now, as we go through this question, I don't want to do that sort of calculation. 0.79 times anything, unless that anything is really nice, 0.79 times anything is just going to become a horrible calculation. We're going to look at ways to make this nicer so that I can get through this question, get to the right answer, but also get to the right answer in a reasonable amount of time. Now, the other thing that we can tell from this is that he sold a total of 214 plates of hummus and packs of pita. So really, we've got a limit there. We know that these two need to add up to 214. So every time I add a plate of hummus, I need to take away a pack of pita, and vice versa. Every time I add a pack of pita, I need to take away a plate of hummus. Now that gives us some indication about what's going on in the question, because Bo makes more money for a plate of hummus than he does for a pack of pita. So every time the number of H's goes up and the number of P's goes down, then Bo's profit is going to increase. And every time the number of P's goes up and the number of H's goes down, Bo's profit is going to decrease. So there is going to be a maximum profit. Bo's biggest profit is when he's selling as many plates of hummus as possible and as few packs of pita. And the reverse, Bo's minimum profit is when he sells the most packs of pita and the minimum plates of hummus. Okay, so let's take all this, take a look at statement 1 and see where we get to. So Bo sold more packs of pita than plates of hummus yesterday. So packs is bigger than H. All right, so what I want to do here is do something called sort of testing the extreme values. Like we've just said, as P goes up, then Bo's profit is going to go down. So the first thing I want to look at here is what will happen when P is as small as possible. So the smallest P can be, and still be bigger than H, and still have H plus P equal 214, is when P is 108 and H is 106. All right. Now what's going to happen here is if I do this, if I do a bit of calculation, figure out the amount of profit Bose makes in this scenario, and it's under 700, then we're done with statement 1, because all I can do now, this is the smallest P can be, so I could make P bigger, but as I make P bigger, Bo's profit is going to decrease. If it's already under 700, in the scenario when his profit is as big as possible, then it can never be bigger than 700 and statement 1 will be sufficient. But let's jump in and take a look at this scenario. So like I said, I don't want to do 108 times 0.79. That's going to be horrible. What we're going to do here is I'm going to underestimate a lot of values, and if I underestimate and the overall value is still under 700, still over 700, I know the real value is definitely bigger, so it's definitely over 700. So I'm going to underestimate the number of packs of pita he sold. I'm going to underestimate the amount of profit that Bo made for each pack of pita, and I'm going to say that Bo made $70 on each pack of pita. Now here for the hummus, I'm going to keep the 106, and I'm going to underestimate the profit he made for each one and say that that's just going to be $6. Now 106 times 6 is going to give me 636, which means that the total here, 70 plus 636, is going to give me $706, which is more than 700. But I've underestimated the 100, the 70, and the $6. I've underestimated all three values, and the final value I get is still bigger than 700. So if these were the real values and were all bigger, then the actual value that came out of this would be even bigger. It would definitely be bigger than 700. Okay. Now, what I need to do to demonstrate that this is insufficient, now I'm doing the reverse. If this had come out to be under 700, we're done. Statement 1 is definitely sufficient. It came out to be over 700. So what I need to do now is go down to the other end and say, well, what happens when P is as big as possible? If that is under 700, I've got one scenario that's over 700, one scenario that's under 700, and statement 1 is insufficient. Now let's make P as big as possible. There is nothing in the question that says that, or I don't think there's anything in the question that says that Bo definitely has to sell at least one plate of hummus and at least one pack of pita. But I'm just going to hedge my bets. I'm going to be a bit careful, and I'm going to look at what happens when P is 213 and H is 1. Just in case there is something in the question that says that they must sell at least one. I don't think it's there, but this is the GMAT. I'm just going to be careful and try not to make any unnecessary mistakes. Now in this calculation, we're going to reverse things. If I overestimate some values and the outcome I get is under 700, well, I know that the real value, because I overestimated, the real value is even lower. It's definitely under 700. So what I'm going to do here is say, I'm going to keep P as 213. I'm going to say that Bo profited by $1 for every pack of pita he sold. So that gives me a total of 213. For the plates of hummus, you can probably see where this is going. I've got so much room under 700. For the plates of hummus, I'm going to say that Bo profited by $10 for every plate of hummus he sold. So I'm going to get a total of $10 profit, which will give me 223. Now I've overestimated the amount of profit that Bo made for each plate of hummus, pack of pita, and the actual value has still come out to be under 700. I know the real value, because of my overestimation, is even lower. So I know the real value is definitely under $700. I've got one scenario over 700, I've got one scenario under 700. That means statement 1 is not sufficient, and I'll cross out A and D, and the answer is going to be one of B, C, and E. Okay, statement 2 next. Bo sold fewer than 64 plates yesterday. Plates of hummus, so plates is H. So we sold fewer than 64, so H is less than 64 here. Well, again, that idea of testing the extremes, I've already got one extreme. H is as small as possible, and this is definitely under 700. Let's make H as big as possible, and if that is still under 700, then every value of H that satisfies statement 2 will be under 700, and statement 2 will be sufficient. So the biggest H can be, and still be less than 64, is when H is 63. And when H is 63, in order to make H plus P equal 214, then P will need to be 151. All right, so again, I want to show that this is under 700, or at least that would be nice. So what I'm going to do is overestimate some things. I'm going to say that if H is 63, I'm going to times that by 7. So I'm going to say that the amount of profit Bo makes for each plate of hummus is 7. Now 63 times 7, I could make that a bit nicer by splitting that into 60 times 7 plus 3 times 7. That's 420 plus 21, so 441. Now I've got quite a bit of room here. For the packs of pita, I've got 151 of those, and let's say Bo profits by $1 for each of those. So Bo's profit for his packs of pita is 151, which gives me a total 441 plus 151 is 592. And I've overestimated those values, and what has come out is 592. I know the real value is even less than 592. I know the real value is definitely under 700. I know the real value at the other extreme is definitely less than 700. So if Bo sold fewer than 64 plates of hummus yesterday, then he definitely made less than $700 profit. That means statement 2 is sufficient, and so the answer to this question is going to be B. All right, like I said up at the top, this is horrible. I don't want to do that sort of calculation, and so if I can use it's not intuition. It's sort of thinking about its number sense. It's knowing that his profit is going to increase as H goes up. His profit is going to decrease as P goes up, and it's about knowing sort of what am I trying to show. This test the extreme values. What between H being 106 and H being 1, the values are going to be somewhere between 706 and 223, and I'm going to cross that 700 line. If I cross that 700 line, it's insufficient, whereas in statement 2, I've got one extreme is under 700, the other extreme is under 700. Everything between these two scenarios is going to be somewhere between these two values, and so everything's going to be under 700. That makes it sufficient. All right, so if we think about what we've done across the course of this video, there are times, and there are plenty of questions where a good knowledge of arithmetic is going to be really helpful, but that will only take you so far. And really, when things get nasty, I want to find ways around the arithmetic, whether that's by testing extreme values and doing a bit of estimation as we've done in this question, or whether that's by sort of finding common factors, or just making the calculations nicer like we did earlier. There are ways to make the arithmetic in the GMAT just that little bit nicer, and that'll mean that you make fewer errors and possibly get through the questions you get through the questions more efficiently and reduce your chances of making mistakes. All right, that's all I've got for you today. If you've enjoyed this video, please hit that like button, please hit that subscribe button, and we hope to see you back here at one of our other videos very soon. Have a great day, everyone.